Work and Power, Part 2, the sequel. What happens in terms of work when the applied force and displacement are not in the same direction? So in that previous case where we dealt with pushing an object, force was in that way, displacement was in that way, so obviously work is done on it. What if it's not in the same direction though? For example, if we have a scenario like this, this stick-figured dude is pulling this box in this direction, but, and of course we can see that the box is moving in this direction, so delta D, or the displacement's there, and yet the force is this direction, angled. So it doesn't take too long to figure out that. Well, we'll have to find the component of the force that is working in the same direction as the displacement. And we've done this before with vectors. So we can think of that force vector as being broken down into a Fx, a horizontal force component, and an Fy, a vertical force component. And if we can figure out that Fx, that is the force that's causing this. So pulling at this angle at a certain force gives us a smaller force which works in that way. So if we take a look here, determine the horizontal component of the applied force which is in the same direction of the displacement, or as the displacement. So that is the force component that we'd be looking for. Whenever you're pulling at an angle, what part of that is effective in going in the same way as the displacement? So if we take a look at that, of course this is not new. We've done this before. That, of course, the cosine law would be beneficial in doing that. Whatever force we're pulling it with at an angle, we have Fx and F, just some plain old F there. So cos of theta would be Fx over F. Solving for Fx, multiplied side by F, we get that relationship, which we can use all the time, really. So this can be substituted into the work equation. So instead of using W equals F multiplied by delta D, we could use F cos theta delta D. And we could actually use that anytime. Because if this angle is 0, the cosine of the cos of 0 is actually 1, so it doesn't make a difference. So you could blindly, I suppose, use that all the time. Or if you didn't want to, so as our previous case, when F and D are in the same direction, it's just simply work is equal to force times displacement. When we're talking about another angle, though, we have to use this idea, finding that component, assuming that the angle given is the angle from the horizontal upwards. You can use that formula there. Or we can use that all the time, once again, because the cos of 0 is 1, so it won't change anything. So work equals force multiplied by displacement, or work is equal to force multiplied by cos of theta multiplied by displacement. So here I have an example here dealing with that idea, applying a force at an angle. So here we have a wagon is pulled positive 20.0 meters along a level surface. If a force of 60 newtons is applied on the handle at an angle of 15 degrees with the road, how much work is done on the wagon? So, looking at that, once again, the angle is to the horizontal. So, of course, the first thing you should likely do is sketch that out. That always helps. So I drew a little funky wagon there. So it's being pulled at an angle of 60 newtons, 15 degrees to the horizontal, Fx, Fy, and of course the wagon's moving that way. So once again, we have to find the component of force that's effective in moving that wagon to the right. So W equals F multiplied by the cos of theta multiplied by delta D. So looking at that, we have our applied force of 60 multiplied by cos of 15 multiplied by 20.0 meters. So we get 1,159.110922 Newton meters. And of course, if you take a look here, I think we have, let's see here, we have 3 sig figs throughout, so we have to keep 3 sig figs. So 1, 2, 3, that's a 9, so that gets bumped up to a 6. And of course, we have to ensure that this is still in the 1,000s place, so put a placeholder 0 there. 1,000 160 joules. Okay? Now, you may be remembering that first video, that weird scenario involving zero work done, when you have force and displacement at right angles to each other. Take a look here. Here's the reasoning. No work is done when F and D are perpendicular, because using this equation, you can see work is equal to F multiplied by the cos of theta multiplied by D. So if we use 90 for that angle there, the cosine of 90 is, of course, 0. So we would get 0 multiplied by all those other variables and 0 joules. And it makes kind of sense that you wouldn't, because that force is not doing anything in moving that object perpendicular. So we could say the force is not effective in the movement, therefore it's 0. Or mathematically it works out cos of 90 is 0.